Yeah, would you mind pulling it up? I'll kind of say what slide number we're on as we go, but I think I'll just press on. And then great, thanks. Okay. 1 second here. All right, so we're still on slide 29 here. Using this method, I drew a line through each shockwave on the top and the bottom of the model, and then measured the angle to the center line and recorded those. Now, for the test, we had 19 images, each spaced out at 400 microseconds apart. And what I found was that the shockwave for those 38 measurements, so top and bottom, the shockwave angle was 37.7 degrees with a standard deviation of just over 1. And the Mach number calculated from that angle was 2.44, and the standard deviation on those was 0.085. So within a standard deviation, the actual Mach number is most likely between about 2.36 and 2.52, which is pretty close to the design constraint. Now, because of there's a number of reasons why it's not dead on. One of them is probably there's a good amount of error from this measurement method, and probably using pressure measurements would improve the accuracy of this measurement. And then also, viscous effects weren't taken into account in the design of the nozzle, and the actual tolerances on the machined nozzle are wide enough to cause a similar deviation Mach number. But I think that the primary goal of validating supersonic flow is achieved with this analysis. So one thing that you guys may have caught, it happened pretty quickly in that video, but it slowed down a little bit here. This is on slide 30. On startup of the nozzle, flow. When the nozzle started, flow went into the chamber, and as it went into the chamber, expanded, and then eventually hit the wall, and then normal shock was forced to form and propagate back through the chamber. So what I actually found was after exactly 7.6 milliseconds of operation, a traveling normal shock came back through the test rhombus. And that normal shock acted for about 5 frames, so probably only about 2.5 milliseconds or so. And then shortly thereafter, the flow began to restart again. So it actually as it went, the propagating normal shock wave slowed down, and just out of frame. So just out of frame right here is the nozzle exit. So the normal shock is getting closer and closer to the mouth of the nozzle. So the flow stopped briefly and then restarted. But as it was restarting, here on slide 31 now, the diaphragm which ruptured came through the test section, which was planned. But because it didn't rupture into small pieces, it became adhered to the model and drastically shortened the actual useful test duration for this test. But what can actually still be seen is in front of the model, there's a visible bow shock right here. So it's clear that supersonic flow is continuing through this process, but I can't actually calculate the Mach number because the geometry of the model is not really known. So it's clear that supersonic flow is seen during this time, but the problem of the diaphragm being ingested as a large piece will have to be solved to increase the test duration. So the diaphragm, initially as those pieces of diaphragm fly by, that was observed for 4.8 milliseconds. A detached bow shock was observed for a pretty steady state of about 6 milliseconds. And then the amount of time from the first time oblique shock waves were seen to the last bow shock wave was seen before the nozzle unstarted was 32.4 milliseconds. So now comparing that 32.4 milliseconds to what the same analysis that was done to initially calculate the test duration. The test that video was from started at a chamber pressure of 25 torr. Now, the higher the chamber pressure at the start of the test, the shorter the test duration, because with the same mass flow rate, that pressure that unstarts the nozzle will come sooner. So using the Mach number that was measured with a line, a line above and below, which is plus or minus 1 standard deviation of the calculated Mach number, I calculated the test duration against the initial chamber pressure. So for an initial chamber pressure of 25 torr, that puts the test duration is calculated with my method between 52 and 74% of what was calculated. Now within that number, there were a number of other things that happened with the shock reflection and the diaphragm coming in, but this would be just how long supersonic flow was attained by the nozzle. So it's kind of like the upper end of what could be done on a test if 1 or 2 problems are solved. So to conclude, a novel type of supersonic wind tunnel was conceived, designed, built, and then validated for a Mach number of 2.44. The vacuum chamber and as well as a vacuum chamber was refurbished and brought to operation, and with a few more modifications and additions will be useful with the air department as well for vacuum testing of various hardware. The test section diameter of 7 inches. The test duration in which clear, steady state supersonic flow was observed without any other issues. So combining when the oblique shock waves were observed in steady state and when the bow shock waves were observed in steady state was 13.6 milliseconds. And the entire time when supersonic flow was developed just with a number of perturbances in the flow was 32 milliseconds. So moving forward, there are a number of things that can be added and a good amount of work that can be done in the future using this. So the primary goal, the biggest thing that I hope is done, is that a lot of students use this tunnel for supersonic testing with various projects and other research opportunities. Now that's the primary goal. But in terms of actually adding to this chamber and making it and improving its quality as a wind tunnel, the model mount can be improved. So this was just, I just used a bunch of various pieces of 80-20 to aluminum to mount it in place, but there's not really any control over the angle of attack and the side slip angle of a model. So optimally that would be able to be done remotely, so it could be varied outside the chamber without having to open it up between every test. But that's one addition. Improvements to the shadow graph system. So I think that specific lenses or mirrors should be purchased to increase the diameter that can be viewed, since the diameter we viewed was really only about 2 inches, but up to around 6 to 8 inches diameter would be optimal. And then also improve the quality of the images that are taken. Feed-throughs, so electrical and then data feed-throughs should be added to the tunnel to allow for different data acquisition, so to be able to measure pressures and temperatures within the test section. And then also to power a better light source from the inside. We had to use just a battery-operated light source in the test, but we can get much brighter and film at a faster rate with more light. New nozzles and different nozzles can be designed, so to hit different Mach numbers and to have different quality of flow. So we can have different size nozzles, Mach numbers of like 2 or 3, and then also, since this nozzle design was so simple, like further nozzles can be designed using the method of characteristics and taking more things into account in their design. The diaphragm method should be improved, so the diaphragm and diaphragm burst method should be improved. So there's a number of ways to do that, but the problem with the diaphragm being ingested as one large piece going through the test section needs to be solved. And then a couple better burst methods can be developed. The chamber needs some dedicated vacuum hardware. So the chamber that we use, or we basically borrowed everything vacuum related from the Space Environments Lab, but it'll need to operate as a lab and to operate has its own facility. It'll need some like vacuum pumps and things like that. Force balance can be added to be able to measure forces and moments on models. And then particle image velocimetry can also be added, since for supersonic flows it's typically very difficult to perform PIV because you need to seed the flow with small particles, which you then view after passing a laser through them, you view with a camera. But supersonic flows are typically really difficult to seed, but because this chamber opens to the outside, it should be relatively easy to seed the flow, as you can just basically fill the area around the chamber with the seeded flow and it'll be drawn into the tunnel. But that concludes my thesis project. Thank you guys for coming.
So we invite questions from anybody, but particularly the committee members that are in the room.
Were you able to hear that, Damon?
No.
Oh, so Dr. Doig just opened up for questions from anybody, and particularly from committee members.
Got it. Hey,
Yes.
I had a question about the cellophane thing.
Okay.
So do you have any ideas about, I think you're saying cellophane went down your tunnel, got stuck on the leading edge of your test article?
Yes.
And then as a result generated a bow shock?
Yes.
Do you have any ideas about why that would happen?
I do. So
You want to just repeat the question?
yes. So just to repeat the question, Damon's asking why I think that the cellophane didn't behave as the literature would suggest, and why it ruptured as a large piece rather than breaking up into small pieces. So there were, I truncated some of the, or to go over every single minute detail of the project would have been taken hours, but one of the problems that we had for testing was that the diaphragms would slip out from between the inlet bell and the inlet adapter where they were clamped, and it was found that one of the pieces, the machinist who made it, didn't machine a smooth surface, like a flat surface into one of them, so it would grip the diaphragm really tightly on one side and loosely on the other. So as we got to low pressures, the diaphragm would slip out. So before we got to the test pressure we needed, it would slip out, rupture, and then flow through, and we'd have to reset and repump. So the design diaphragm thickness was to have 0.04 of an inch of cellophane or 0.01 of an inch of mylar. But we found that the only way to keep the diaphragms from slipping was to add diaphragms. So the actual test was performed with 5 diaphragms for a total thickness of 1/10 of an inch, rather than 4.
100.
Yeah, exactly. So it was a lot thicker. So because there was more diaphragm than there should have been, the stress state in the diaphragm itself was significantly more relaxed than it would have been. So instead of being at 90% of its ultimate yield strength, the diaphragms were probably only at 40 to 50%. So my theory is that if we can fix the diaphragms from slipping out from between the inlet bell, and you can reduce the thickness of the diaphragm, when the stress that's in the diaphragm itself is much higher, when you rupture, it should rupture into smaller pieces. Kind of like popping a balloon, where if you pop it when it's fully inflated, it shatters into small pieces, but if it's only half inflated, you just kind of get a hole in the side of the balloon.
And you think because there was so much diaphragm material that when it hit the model, it kind of retained its shape, which would generate the bow shock?
Well, so he's asking if because there's so much material, that's what caused
I
it
guess
to.
I'm just surprised. Sorry, I cut you off. But I'm just kind of surprised it wasn't just, conformed to your model and kept the sharp clipped shape.
Yeah, so I'm not sure exactly why. It could be just the number of diaphragms or the thickness of the material caused that. Also, unsteadiness, you can see the diaphragm flapping around at the tail. So at the tail end of the model, you can see it flapping up and down. But basically, the model has a pretty sharp front edge, which is blunted a little bit now because I kept shooting it with diaphragms. I think it would be significantly rounded. But I don't think that the problem with the bow shock was caused by the amount of material. I think it's caused by the diaphragm being in too large of a piece. So I think that if we can figure out a way to get the diaphragm to rupture into smaller pieces, that problem would get mitigated, and the small pieces wouldn't adhere as readily as the large piece.
Huh. Just out of curiosity, did you look at the Mach number at which the shock would have detached from something of this angle?
Of this, so of that, you mean the angle at which the flow would have detached at this Mach number?
As Mach number goes down, there's some Mach number where you no longer have a detached wave shock. You have
Right.
a detached shock, which is what bow shock is.
Oh yeah.
I'm wondering if an alternate explanation could be that for some reason your Mach number was lower, and that's why you got bow shock. But anyway.
That is possible. It should. I think it's about Mach 1.4 if I'm correct for air. I believe that under 1.4 you can't really get an oblique shock waves, as you just have a detached bow shock. So that's possible. Yeah, that's possible. I did not look into that, but
Okay.
yeah.
You had a question at the back?
Yeah.
Yeah, I had a question on, I guess it might have been lenses that you
Mhm.
used. You said when you got them, they weren't quite as convex as you wanted
Right.
to be. So how much do you think that could have affected it? I know you said you were still able to do measurements reasonably.
Right.
I'm just curious, like how
Right.
real is this?
Yeah. So basically, so if you think back to geometry for a parabola, if you have a parabola has one focal point. So that's like the shape that's usually used for dishes for like focusing like a radio signal. Is if you have a collimated beam or like parallel rays come into the parabola, they get focused onto that focal point. So one of the lenses has a parabolic shape on its curvature, so it was reasonably well able to produce a collimated beam starting from a radial source. But the other one has a spherical curvature. So when you use a spherical lens, you introduce what are called spherical aberrations in the image. So you get a lot of distortion, and it kind of makes it so that the light doesn't focus down into one point. It focuses down onto a number of points that spread out in the long axis of like the direction the light is going. So you're not able to focus the image the way you're supposed to. So you end up having a distorted image. So I think that was probably the biggest thing, was that one lens, one of the focusing lenses, was not of the optimal curvature.
Ignoring all the other things where you have the reflected shocks and the diaphragm issues and whatnot, does the Mach number of the flow in the test section change as the pressure of the chamber comes back up to be equal?
It does not change until the pressure in the chamber exceeds the exit pressure of the flow. So because the flow is moving...
Can you
Yeah. Oh, repeat the question?
just, can you repeat? Yeah.
Sure. Yeah, so there was, so there was one question. The previous question that I answered was about the, why I think the images were distorted with the lenses and what kind of lens would be required. And then Dr. Gregg just asked
I got that from your answer.
Dr. Gregg just asked if the Mach number of the flow would change as the pressure in the chamber rose. So, up until because the flow is supersonic, the pressure in the chamber is incapable of affecting the condition like at the throat and through the nozzle, because the rate at which pressure information propagates through the flow is Mach 1 and the flow is going approximately Mach 2.5. So what can happen though is as the pressure rises, the pressure pushing in on the outside, like around the nozzle, so kind of like radially into the side of the nozzle, so that's just the stagnant pressure of the chamber. When that pressure exceeds the pressure of the flow, then it starts to be able to push into the nozzle, and then that impacts what Mach number is reached because it effectively reduces the exit diameter of the nozzle and kind of truncates it down. So up until the point where the flow shifts from being underexpanded, it's not counting for the propagating normal shock, the flow isn't able to be impacted by the pressure of the chamber. But once that point is reached, then it does.
Okay, and so did you say what pressure that was? that?
That pressure, it's somewhere. I couldn't say off the top of my head.
Is that in the thesis?
Yeah, it will be if it's not. I'll check. But it should be.
Note that.
It's I think it's on the order of 60 torr. So this was starting at 25 torr, but it's on the order of like 50 to 70 torr was when this nozzle would become overexpanded. Yes.
What's the lowest pressure achievable, and how long does it take to turn around the test at 25 torr?
Oh, that's a good question. Oh no, I didn't include it. So the lowest pressure. So we did so the question, Damon, was what's the lowest pressure achievable by the chamber, and how long does it take to turn around a test? So we did a full pressure test where we just stacked a number of diaphragms onto the inlet to make sure it wouldn't burst or slip out, and then ran the vacuum pump for 2 hours just to see what pressure was attainable, and we got to 1.5 torr, and it took about 2 hours to reach that pressure. Now there's a number of additions that need to be made to the chamber. Like I mentioned, we were kind of by hand sanding and polishing the many sealing surfaces of the chamber. But with some improvements for those, we can probably reach a lower pressure. So but to get a good test, you don't necessarily need to reach the lowest pressure in the chamber. What I found was that for pressures between 15 to 25 torr, you have should have plenty of super time with your supersonic flow to achieve a good test. So if we were going to, it takes about 30 to 35 minutes to pump down to 25 torr, and it took us about 3 to 5 minutes to reset the diaphragm and the diaphragm burst method and everything like that. So we were able to do probably a test every 45 minutes if we're going through and not having to make model changes and things like that. So within 3 hours, you can probably do 4 or 5 tests. Yes.
So for the test rhombus, on both of the sides of that kind of test section area, those are shock waves?
So the question was if what's on the side of the test rhombus are shock waves. So it's actually slightly different. It's called a Mach wave. So it's not technically a shock wave. What it basically is like the weakest. It's the line that the weakest possible conceptual shock traces through the flow. So what this actually is if anyone who's taken compressible flow, if you've looked at Prandtl-Meyer expansion fans, there's a beginning line and an ending line to the expansion fan, where it's like between that region the flow turns and expands. This is that inner line. So it's basically it's just the area of influence of the flow, but there's no shock occurring. It's just the flow is expanding and turning out into the chamber.
Okay, so there's an acceleration.
Yeah, so it's accelerating. So everything out here is accelerated at a higher Mach and is at a higher Mach number than what was at the exit of the nozzle. But everything that's inside is at the test condition.
That's right. You said it was under expanded.
Yep. Yes.
So it's 23.6, the Prandtl-Meyer angle, corresponding to the Mach number of 0.4.
For 2.44, yes.
Sure.
Worrying me. I was sure.
Like 36.
Is it really? Are you?
I looked it up.
23.6 for air at Mach 2.44. So, okay.
But I think you're correct. You're just saying it wrong. I think you measured 36 probably. I'm assuming you did this a while ago, but along the conical wall, right? This is what you did. It still doesn't add up exactly to the right thing. It's pretty darn. It's within a couple of degrees.
Oh, I see what you're saying.
Is this what you did?
That because the flow, you're saying that because the flow
It's not
right
horizontal.
here
Yeah,
is not horizontal. When I did this calculation, I assumed axial flow. I was not taking into account.
No, I think you assumed conical.
Okay.
We can double check.
We'll double check that number. Yes.
When we were originally discussing the concept of this, one of the things we were worried about was condensation of the flow, which
Yes.
you didn't seem to see any evidence of in the the limited high-speed visualization we have. Do you have an indication, or did you do any kind of counts that didn't really show up in the thesis of at what point would that occur, or crystallization, or anything else
Sure.
that might happen?
Sure. So Damon, the question was there was some initially in the conception of the thesis, there was some concern that because we were drawing air from atmosphere, which has some non-zero humidity, that as the temperature decreased, that water would condense out of the air and impact the test condition. So we did not observe any condensation, and Dr. Doig was asking if I was able to calculate exactly when that would occur. So actually, the temperature and pressure that we reached is well below the condensation point for air. But the literature, so using Pope and Goins' book on supersonic testing, they've shown, or they discussed that when you can subcool a flow, so bring it below the temperature at which condensation would occur, but if it happens quickly, condensation doesn't always show up, because what's required for condensation is not just that the water becomes a liquid, but that the water particles are able to find each other and condense into droplets. So we can't actually see like infinitesimally small pieces of water, but we can see droplets. So the idea, so it's most likely that farther in the chamber, the water is condensing and collecting into droplets. But because this happens so quickly over such a short distance, because it's happening over such a short distance, the water is not able to condense into droplets. So I don't actually know I did not do an analysis to find out exactly when that could occur, because I don't know, I would have to research on how to do that. But that's the logic behind why we didn't see condensation.
I wonder if a test was done where the surrounding air was quite dusty in the level of humidity, then you would see
That's possible.
that, because they would have already agglomerated together on a dust particle or something like that.
That is definitely possible, because I think water tends to need something to attach to. But because it's going so fast, just over this short distance, I don't know. I have to calculate exactly at what point.
I'm more thinking about like an ice crystal comes into the pressure sensor that we may mount
Gotcha.
later on and damage it or something like that.
Yeah. So I would have to look at exactly when that would happen. Right? Yes. So I'd have to look exactly when that would happen, but I did not calculate that. So I think it's pretty non-trivial trying to predict when that would occur. Yes.
So I know you attributed the model damage to the diaphragm,
Mm-hmm.
but is it in that proximity to the ground and will worry you for breathing?
Yes. Okay. So Damon, the question was that so there's some damage, some blunting and denting on the leading edge of the nozzle. It started off very sharp and is now kind of dinged up. And he was asking if that was as a result of just indrafting air that's close to the ground and kicking up dust and shooting potentially dust or particles through. So the answer to that's possible. I was attributing it to the diaphragm because it's really clear that the diaphragm definitely impacted. And I'd also think that I didn't, in examination of the inside of the chamber after running tests, didn't find any large particles. There was some dust that was ingested, but didn't find any bits of rock or anything that would suggest to me that that's what caused the denting. So I think it's the cellophane, which even though it's light and small, moving really quickly. So I think that's what it is. That's a good point. Yes.
I was a bit concerned about the sting itself. I know you said you just put it together, and that was not, did not give a lot of time to it.
Uh-huh.
It looked really blunt to me, really close to the model.
Okay.
Do you think there's any communication between the front end of that sting?
In terms of vibration, or sorry?
There's certainly going to be it's so blunt. There's going to be a normal shock that's going to establish.
Definitely. So
especially the base of it.
Especially the right here.
No, the bottom.
Oh, here,
Yeah,
right here.
Yeah.
Oh, yes, that's a good point. So yes, there's definitely a shock. There must be a shock standing here in front, but the distance that it would have to stand off from this model, I think, is too great to actually be viewed by what we looked at. What we actually saw, because the lenses were kind of small, was just this front piece. So I think the normal shock from here would have had to stand
Right.
all the way
So
through.
roughly how long along the wedge do you image?
So that was it was about 1.5 inches. About 1.5 inches, and the model's floating around here somewhere. I'm not sure where it went, but so about 1.5 inches. So we only reviewing probably up to about here.
About a third to
Yeah.
half of the wedge.
Yes.
I noticed also that the port windows isn't well imaged on both sides. It's very sharp on the downstream end, but on the upstream end, you start having an aberration. Was it not possible to image the entire window port? You don't have a perfect circle there.
Right. Yeah. So that was probably due to, or that. So, Damon, the question was that the image that we took wasn't perfectly circular. So I think that was probably due to Kona I believe it's called Kona aberration, which would be from slight misalignment of the lenses. So we actually the setup was likely not perfectly lined up, and because it wasn't perfectly lined up, you can get some distortion in the shape of the overall image. So this was most likely focusing into the camera lens itself, and some of it being blocked by the shutter of the camera, by the aperture in the camera lens. So we had a couple problems with the actual lens. So one of the petals on the camera aperture got stuck open. We ended up having to flip the camera upside down to kind of get it to mostly retract. But I think some of the image probably did not make it through the aperture.
So you're saying that the curve that we see there, that's not the window, that's the edge of the lens?
This is not the window. Sorry. This is not the window. This is the collimated beam passing through the test section. The window is much larger. So the collimated beam is only 2.5 inches diameter.
And the left-hand side is the aperture.
And I think the left-hand side is the aperture, yes. So this would be the edge of the beam, and then, yeah.
Is there, and I know we looked at that tank many times, and I can't remember right now, is there no orientation where we can have a port on both sides of the line?
We may be able to. So there is, let me see. Okay, so on this flange right here is not perfectly aligned with the window, but it's fairly well aligned with it. So
There's an overlap.
there is an overlap. So I think that we could replace this with another window and be able to have better mirrors out external to
Yeah,
it.
that sounds like a much better idea.
Yeah. I think that would be a good idea in the future. But yes, that it lines up fairly well enough, I believe, to be able to pass a beam from one end.
Is the
outside.
plan to leave the whole facility outside, or Graham, are you planning to move this inside somewhere?
I don't think we have anywhere to move it inside, but it's up to Dr. Gregg where she wants to.
No, it's outside because we literally cannot fit it in any of our labs. So it's got a little